Hi, I think I've worked out what's wrong. Okay, what's happening? We need to be really careful with what you're putting in the chat, basically. If the word C, if the C word goes in the chat, then I think the YouTube sensors are kicking in and switching it off just in case we're giving this information. So probably you're not in here yet. So this is first years, okay? What I had to do was stop the stream for this first years and then start this one because it cut that one off. So I'm going to do an hour of first years first. I'm just going to push on and hope that the first years have found me, basically. So yeah, no mention of the word in chat, please. Vectors. So first years, we're going to be working on vectors. This is not an easy topic. It's a difficult topic. It's not the sort of thing that I can just do in half an hour and then you're like good to go and you can do all the questions. Okay. There's lots of things that are like that in the math syllabus. Vectors is not one of them. So the actual stuff you need to know is not that huge. You need to know, well, let's have a look. Where's the vectors? We have talked about this week all of exponentials apart from the linearizing data with logs, which we'll do in a couple of weeks. We've talked about finding the equation in the normal, the tangent and the normal, the fact that stationary points are where the derivative is naught, the fact that stationaries can be split into maximums and minimums, and you need the second derivative to work that out. The fact that optimization problems are basically just stationary point questions, and first principles is something you need to learn. That's that limit as h tends to naught, but of f of x plus h minus f of h, blah, blah, blah. But I think now all of that probably was covered in college, so that's not new stuff for most people. The integration we talked about yesterday, I did a really brief intro, but then talked about a lot about areas under curves. We also did trig this week. So look how much work we've already done this week in 1 hour a day. And the Monday was just the overview. So that's Tuesday, Wednesday, Thursday. Literally, those of you who've been coming every day, well done you. It's just an hour a day is a really good investment in your future if it's going to involve maths in any way, which we don't yet know. By the way, I have had insider gossip by my contacts about how your A2 grades are going to be assigned. I'm not sure when that's coming out. It might be today, it might be next week. If it comes out today, then we'll be straight on it because we know we've already discussed it and stuff, and we'll let you know as soon as we're allowed to let you know what's going on. I don't know when, I don't know if it's been 100% agreed with everybody, so we're waiting to find out at the moment. Okay, right, today is vectors. It's not that important, it's not important as the red ones, but it's quite a big topic. You don't need to know that much. You need to know how to find the length and how to find the direction of a vector. So the length you find with Pythagoras, you look like a stick like this, and you just do this squared plus this squared, square rooted. And that's for 3 dimensions as well. If you're in the second year, exactly the same. You've got a stick like this, that's the vector, and you do this squared plus this squared plus this squared, square rooted. Just Pythagoras in 3 dimensions. In 2 dimensions, we can talk about direction in a way that's more complicated in 3 dimensions, so you don't have to worry about in the second year. In 2 dimensions, you can talk about what direction the stick is going in, the vector. And it's annoyingly complicated because if I say that way and I point at the corner of my room, what direction is that? Relative to where? Are you talking about the direction relative to straight in front of north, or like what relative to what? So direction, we need to draw pictures and use trigonometry, but with a picture. It's annoying, direction. It's not a clear concept, which is why a lot of students find it difficult. Unit vectors, they're just ones with length 1. Unit, yeah, 1, length 1. So length is Pythagoras. If it's got length 1, it's a unit vector. If it hasn't got length 1, just divide it by its length, and then it has length 1, done. And for the angle between vectors, you need to use the cosine rule. This, by the way, this is literally all you need to know. I, J, and K are the way that we describe vectors. So you can either describe it in a Cartesian way, which is where you lay them all out horizontally, and you say how many I's, how many J's, how many K's. K's for the second year. First year, just go I's and J's. And then that tells you how many that way and how many that way. Or much nicer for 2 and 3 dimensions is to use a column vector. So just how much left and right is at the top, how much up and down is at the bottom. So much nicer than using I, J's and K's. Weirdly, the time when mathematicians use I, J's and K's, we don't use I, J's and K's. So for 2 dimensions, you've got I and J, or you could have 1, 1 like that. For 3 dimensions, you've got I and J and K. And that's the only difference in the second year, by the way. The only difference, nothing that's written on this page changes, and there is no additional learning. There is literally just one more number in your vector, like that. Now, what would happen in 4 dimensions? Well, the vector, you can have massive vectors and matrices that we draw out, got lots of rows and lots of columns. But to be honest, what we start doing is using E1, E2, E3, E4, E5. So if we were in 5-dimensional space, we'd use EK and let K go from 1 to 5. If we were in N-dimensional space, N dimensions, then we'd write E1, E2, E3, all the way up to En. And if we're in infinitely many dimensions, we can use that notation as well. So it's just a notation thing. And I will almost always use vectors rather than Cartesian, almost always. E is, it's a letter, we use it for what's called a basis vector. These are basis vectors. It's just the letter we use. It's like, why do we use X in a quadratic? That's the letter we use. So E is a direction. So E1 is the first direction, second direction, third direction. Like here, first direction, second direction, third direction. Yeah, but N dimensions and infinite dimensions are fun. Right, so playlist wise, for the next 24 hours, we have 24, 25, and 26. Okay, 24, 25, and 26. That's all of the vectors, all done in 3 videos. So it's going to be less than an hour. It's going to be a really good investment of your time. Now, I am going to assume that everybody knows what a vector is, and I'm not going to go over all of the basics. If you want to go over all of the basics, they are in number 24. And there's a couple of examples in 25 and 26, but I'm just going to go through some examples today that cover basically not everything that you might get in vectors, but the vast majority. Okay, so I'm going to start off with a collinear example. Now, everything you need to know is on the left-hand side of the page. As always with the TT notes and with the notes templates, the left-hand 5 centimeters, that's what you need to know. So we don't need to know that much. Collinear, what it means is in a line, the word line there, collinear, in a line. So the idea is if A and B join up, of course they do, A and B join up. If I continue that line, and it goes through C, then A, B, and C are all on the same line, so they're collinear. So the way that I would prove that is I would find out what is the vector from A to B, and what is the vector from A to C. Or I don't even have to do A to B and A to C. I could do A to B and B to C. But what I want to show is that these are parallel. If these 2 vectors are parallel, then they all lie on a line. And that's it. That's all you have to do, show that they're parallel. So the fact that you need is that parallel vectors are one's a multiple of the other one. So that's what I need to do, okay? I also need A to B is B minus A. You use that all the time. The point A to the point B is the vector B minus the vector A. Right, let's do it. A to B. Well, I know A and I know B. A to B is B minus A. Okay, A to B, B minus A. And A to C is going to be C, well, A to C is C minus A. But what's this? I don't know what that is. It's how you get from the origin to the point C. So how would I get from the origin to the point C? Well, I'm told how to do that here. There's the origin to the point C. So that goes in there, 5a minus 4b minus a, which is 4a minus 4b, which is 4 lots of a minus b. So that's all you have to do. All you have to do is show that your a to c is a multiple of a to b. And that means that a to c and a to b are parallel. And if a to c is parallel to a to b, they must all lie on a line. So facts-wise, didn't really need to know much at all. Application-wise, it's always difficult and fiddly thinking in 2 dimensions and drawing pictures and knowing what you need to prove. Next one, prove that J to L. So I want to start at J and go up there and then down. I want to get to L. I want to do J to L. So let's build out J to L a different way. Instead of going straight from J straight to L, I am going to go from J to D, and then I'm going to go from D to L. So that's not really a fact of vectors. It's just imagining a map. If I want to go from my house to my friend's house, I could go via the shop. I could go from my house to the shop and then from the shop to my friend's house. Just moving around, just facts of moving. So J to D. Well, look at this vector, J to D. That vector is literally identical to this vector because J is in the middle. So J to D is the same as half E to D. It's the same movement, E to D, but only half of it is how you get from E to J or from J to D. It's just half of E to D equals 1/2 of E to D plus. Now D to L there is the same as L to F. D to L and L to F are identical. They're both half D to F. It's not fun, this. It's not like solving like an integral or a calculus, like a question where you actually feel like you're doing maths, like trig, algebra, differentiation, integrate. This is like, it doesn't feel as satisfying, I think. It always just feels a bit messy and a bit notationally overcomplicated. It's not that nice, but anyway. E to D, we are told that E to D is D. D to F, I don't know what D to F is, but I do know that D to F is the same as D to E plus E to F. I'm allowed to go via other things. So to get from D to F, I could go from D to E and then from E to F. I could just go, instead of down there, I can go dun, dun, like that. Now D to E is the opposite of this one. E to D in that direction, so D to E in the other direction would make that negative. So D to E is minus D. And then E to F, well, we're told in the question that E to F is the letter F. And then you just expand that out and you get a half F. Tick. Good, yes, our D to E would be minus D, exactly. So they're weird ones, aren't they? Because in a way we're thinking about the image and the picture and moving around a shape. But in a way I was just manipulating letters and it feels almost like a trick. It feels almost like I did, you know, those like 3 cups upside down and you move them all around and then you go, which one's got the thing under it? Feels a bit like that, bit like cheating, like I did sleight of hand. And that is one of the things that's difficult about vectors is you can do 50,000 million vectors questions and you still feel like you can't do vectors questions. It's really frustrating in that respect. Okay, so that's a couple of questions that show you the sorts of things that you need to do and how important this A to B is B minus A is. And the second most important thing, what are parallel vectors? Next. Okay, so this side of vectors is much more looking at length and angles. Whereas what we did a minute ago, though I wasn't looking at any lengths or any angles, I was just moving around. So moving around, going in a direction, parallel vectors go in the same direction. Now we're sort of drilling down a bit into a particular vector and how long it is and which way it's going. So I did one of the ones where it's backwards, where instead of me saying, here's the vector, find the length, Pythagoras, find the angle. Instead of that, done it the other way around. I've told you the direction it's going in and I've told you the length, but I want you to work out what the vector was. So how can we do that? Well, magnitude is length Pythagoras. So we know for sure, and this bit is easy, that a squared plus b squared is 5 squared. Okay, the length, that's Pythagoras. It's going, well, I say it's going. I was going to say it's going that way and then that way. So this length is 5. So a squared plus b squared is c squared. But maybe it's not, you see. Maybe it's going that way because a is negative and then that way. But Pythagoras still applies. Or maybe it's a is positive but b is negative. But Pythagoras still applies. Or maybe it's that a is negative and b is negative and it goes down that way, but Pythagoras still applies. Now we look at the direction. Now it says that it is going on a bearing of 300. Now I don't love bearings, but to be honest, at least like there's a rule with bearings. Whereas if I say it's going at 30 degrees to the horizontal, well, I mean, like there's the horizontal. 30 degrees is like a convention that if we say a positive angle, we're measuring it round that way. So if I said 30 degrees to the horizontal, then I guess I would mean this direction. But then, yeah, I guess that's fair, isn't it? If I meant like that way, and that's the horizontal, and that's 30, I guess I would say 150 degrees to the horizontal. So maybe it's all right. Maybe it's all right. Maybe when I say to the horizontal, I mean the positive horizontal, and we know that positive angles measure up. So, but it's confusing. It's annoying because then bearings, they don't measure from the positive horizontal. Bearings measure from north, and they go the other way. So when you're doing a bearing, it's clockwise that's positive, not anti-clockwise, just annoying. Anyway, in this case, that's north, 300 degrees is over there. So that's going to be 30 because the bearing is 300. Oh no, that's going to be 60, sorry, because the bearing is 300. Annoying, right? But pretty much whenever you've got anything to do with direction, you need to be drawing a sketch. I know students don't like it, but it is really, really important. Right, so now I know which of these it is. It's going left and up. So it wasn't that one, it wasn't that one, it wasn't that one, it was this one, left and up. So A is negative, B is positive. Because when I solve this in a minute, I'm going to get plus minuses when I square root. And I need to know whether I want the plus or the minus. So I now know A is negative, B is positive. Fact. Okay, let's form ourselves a little triangle. This is A. Well, A is negative. It's the length of A. This is B. That's 30 in there. So tan 30 is the opposite over the adjacent. What's tan 30? Root 3? Tan 30 root 3? No, 1 over 2. Is tan 30 a half? Let's just do it on the calculator. Tan 30. 1 over root 3. I could use 60. I could do this one instead. I could draw this triangle with the 60. And I could do, what is it? That's 60. That's length A and that's length B. So I could use tan 60 is the opposite over the adjacent. That would get me the same answer. Right, 1 over root 3. So 1 over root 3 equals B over A. So A, let's put the A on that side and root 3B like that. So A squared is 3B squared. And now I can just go into here. A squared is 3b squared, so 3b squared plus b squared is 25. 4b squared is 25. Square root both sides. 2b is 5. B is 5 over 2. Now, what's really, really, really important here is that all of that algebra would look identical without any of these pictures. And that's where students go wrong with this particular topic. They go wrong because they don't like drawing pictures and they don't like drawing sketches, and they try to do the whole thing algebraically. So they'll go, right, magnitude, that's Pythagoras. A squared plus b squared is c squared. And then they'll say direction, that's shift tan. And then they'll do shift tan of 300 probably. And then they might get the a and the b the right way up. They might get the a and the b the wrong way up. And then they'll go all the way down here, sub it back in there, solve, solve, solve. And then we'll take the positive root rather than thinking about whether it's the positive root or the negative root, whether you want 300 or 60 or 30. It's vital to draw the sketch. It really honestly is. It's not that you draw the sketch because you're not good at it yet. And when you get good at it, I think that's what happens. You start thinking, oh, I'm good at this now. I don't need to draw the picture. And that's so not true. I always draw the picture. Every teacher would always draw the picture. When you're good at it, you draw the picture. So I know what B is. I know B is positive because I know the direction it's going in. And now I can find A. So simultaneous equations. A is root 3B. So A is root 3 times 5 over 2. But I know that A is negative. A is negative. So actually that's not true. A is minus 5 root 3 all over 2. So knowledge, tan is opposite over adjacent, and you need to draw a picture when you're thinking about direction because of the 4 different quadrants and the way it could be going. Length, Pythagoras. Okay, find the angle. Okay, cosine rule, angle, cosine rule, 100% definitely. The angle between 2 vectors, or if you're in the second year, the angle between a vector and a particular axis, the x-axis, the y-axis, the k-axis. Okay, X, Y, Z, the Z axis. Cosine rule. Always, always, always cosine rule for angles. Let's draw it. Angle P is at the middle, and then it's going out to R, and it's going out to Q. There we go. This is the angle we want. So we're going to be using the cosine rule, which means that we're going to be needing to find all 3 lengths of side. So we need to find the length of P to R, length, and we need to find the length of P to Q, and we need to find the length of R to Q. And then we're going to use the cosine rule, always the same. P to R. I don't know what P to R is. I've got P to Q and R to P, but I haven't got P to R. All right, P to R. Well, I could go P to Q and then Q to R. That would be the same. So P to Q is 3 minus 1. Q to R, I don't know Q to R. Any ideas? I want to get from P to R. I know how to get from, I thought you would jump in by now, all of you, but there is a lag. So maybe you have jumped in and I just haven't seen it yet because of the lag. Yay, you have. It's the opposite of R to P. P to R and R to P are the same. They're just going the other way. And what I'm interested in is the length. So none of this matters. What I need to know is how far is it, how long is the vector PR, which is the same as how long is the vector RP. So how long is it? 1 squared plus 4 squared square rooted, root 17. Done. Okay, P to Q, the length of P to Q, 3 squared plus 1 squared square rooted is root 10. Now, this one I do need to do some moving about. I don't know the vector from R to Q, but I do know that going from R to Q is the same as going from R to P and then from P to Q. And I know what R to P is. and I know what P to Q is. So now I know what R to Q is. R to Q is 4 minus 5. And I need the length of that, which is 4 squared plus 5 squared, square rooted, which is 25 over 16. I don't know what that is, 41, root 41. Let's try and keep everything exact. So instead of using decimal places and prematurely rounding, let's just keep everything nice and exact. So we've got this length, P to R, that's root 17. We've got this length, P to Q, which is root 10. We've got the length R to Q, which is root 41. Always, these questions about the angle between is always the cosine rule. So you always need to draw a triangle and make sure that when you draw that triangle, this middle one here is the one that's there with the things coming out from it. Otherwise, you'll find the wrong angle in a triangle. So sketch, again, vitally important with vectors. I can't say it enough. Sketching, vectors, vectors, sketching. Cosine rule, triangles, draw a thingy. Okay, so now I can use cosine rule. Now I'm not going to go through all the details of this because cosine rule is boring, but root 41 squared equals root 17 squared plus root 10 squared minus 2 root 17 root 10 cos theta. That is what you would now solve to find that angle there, theta. Always the same. Always, always the same. So, length, Pythagoras. Direction, draw a picture. Angle between, draw a picture, and then use the cosine rule. A to B is always B minus A, or don't forget that A to B, you could say, well, I'm not going to go A to B via the origin, which is what B minus A is. I'm going to go A to C to B, A to C plus C to B. Doesn't matter what route I take to get there, as long as I get there. I think we've got 2 more. Oh my goodness. None of you told me at the beginning because I had got in a flap about the other stream. I just looked at the timer and we're doing an action hour without a timer on. That's really bad. You know what happens if you do that? You get distracted, you start procrastinating, you don't take breaks when you at the optimum time for taking breaks. So you go on too long. The last hour that you did, you don't really get much done, and then you're tired for the rest of the day. Timer, timer, timer. Okay, it's now 12:34. I think we started at like 10 past. So I think we've done 25 minutes. I think we've got another 20. 20. Oh, 29 so far has it been? I can't do that. 45 minus 29 is 6. Oh my goodness, 16. Okay, cool. 16. Right, next. So you need to know what the properties of certain shapes are. And those shapes are a square, a rectangle, a rhombus, a parallelogram, and a trapezium. So the final lesson on your playlist for this particular topic is all about those shapes, what their properties are, like having parallel sides, having sides that are the same length, da, 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 da. When you know those properties, then it all comes back to the same knowledge that we were talking about before. You don't actually need any more knowledge than what we've already discussed. You need to know that A to B is B minus A, or that A to B is A to C and C to B, that you can go via other things. You need to know that length is Pythagoras. Don't need to know a formula or anything, just like in your head, length, Pythagoras. And you also need to know that parallel vectors, one's a multiple of the other. So if A and B are parallel, then A is an amount of B. That's it, that's all the knowledge down there. Obviously, you do also need to know about the shape, because you can't show that something's a trapezium if you don't know what a trapezium is. So I'll talk about the trapezium one, since that's the example, but all of the different shapes and the things that we'd need to check to show that it's a trapezium or a parallelogram or a rhombus or a rectangle or a square are in that third vector thing on the playlist. So trapezium, it's got two parallel sides. It has to have two parallel sides. So this side and this side are parallel. Okay. Now, from this point, really, I'm narrowing it down to not being the other things. So a square has got two parallel sides. It might be a square. A rectangle has got two parallel sides and another two parallel sides, the same as a square, actually. So it could be a rectangle. A rhombus has got two parallel sides. And in fact, it's got another two parallel sides. A parallelogram has got two parallel sides. In fact, it's got another two parallel sides. So how do I know, just because I've got two parallel sides, how do I know that it isn't a square or a rectangle or a rhombus or a parallelogram? The reason is it doesn't have two more parallel sides. Only two parallel sides. The other two are not parallel. That's it. That's all I need to do. I need to show that two sides are parallel and the other two are not parallel. Okay. Let me see if I can get rid of, I think I'm going to get rid of everything, sorry, by doing this, but it's going to be easier than rubbing out because the iPad has a bit of a flip if I try to rub out. Yes, never mind. Okay, so let's draw our little picture. We've got E to F. Let's draw it like that. E, F. And then we've got F to G. Let's go like, I don't know which ones are parallel yet, so I don't know what it looks like. And G to H. Don't know what that looks like. Well, let's just see if E to F, and then G to H, are they parallel or not? Let's have a look. Because if not, it's going to be these ones that are parallel, F to G and E to H. So let's have a look. E to F. E to F is 2, 3. What about G to H? G to H is -1 minus 3 over 2. Now, is one of them a multiple of the other one? Can I get one of them times something is the other one? Yeah, I can. I can. G to H times -2 is -2 lots of this, which is this, which is this. So step 1 is done. Definitely E to F and G to H or H to G, doesn't matter which way round it is, they're parallel. So it's got two parallel sides. And they are E to F and G to H. It doesn't even, like, their EF and GH are parallel, full stop. So now what I need to do is make sure that it's not a square, not a rectangle, not a rhombus, and not a parallelogram, which I'm going to do by comparing F to G and E to H. So F to G, 1 minus a half. Okay. E to H. Well, I don't know what E to H is, but I could do, instead of E to H, I could do E to F, and then F to G, and then G to H. Couldn't I? I could move my way around. Instead of just going straight down E to H, I could go E to F, F to G, G to H, and that would be the same vector. And the reason I'm finding this is to check that it is not parallel to FG. If FG and EH are parallel, then I don't have a trapezium. I have either a parallelogram, a rhombus, a triangle, or a square, and I need to keep investigating. So that's why I need to do this. So let's work out what that is. E to F plus F to G plus G to H equals 2, 3, 2. 3 minus 2 is 1. Right. 2, 1 is not equal to any amount of 1 minus a half. No way. Because for the top to work, I'd have to have lambda is 2. there. If that lambda is 2, then the top is 2. Cool, that matches. But if this is 2, then the bottom is -1, which doesn't match. And if I make the lambda work for the bottom, so that would be timesing this by -2, then the top doesn't work. So there is no lambda. So therefore, and you have to write all this out because it's a proof, right? So therefore, E to H is not parallel to F to G. And therefore, all of this comes together to mean that EFGH is a trapezium. So these ones, I think, are in a way some of the easier types of question, because if you think about the ones that we had first, and well, particularly the first ones, you really do have to sort of think in a way. And these ones with length and draw, you don't have to think loads for these ones, but they're fiddly. There's numbers, there's angles, there's cosine, there's sine, all that sort of stuff. And these ones where you're sort of moving around and finding out whether things are parallel, you keep switching between this notation and that notation. Look, we've got big letters and small letters, and it's just, yeah. And they all seem different, every single one that you do, even though we're not actually needing much knowledge. Weirdly, every single one feels totally different from every other one that you've done. Whereas these ones, if you learn what those conditions are, there's always only 2 things to check. So have a look at that video, make some notes on that, and then hopefully you will like these questions and you'll be pleased if one of these comes up. Prove that something is a trapezium or a square or rectangle or isn't a parallelogram or that kind of thing. Last but not least, mechanics. Now, there's nothing new to learn when you apply vectors in mechanics, or I should say it the other way around, that you're applying, no, it's that way around. You're applying your knowledge of vectors to a mechanics problem. And really, the only thing that you need to know is that velocity is the direction of travel. So if I tell you the velocity of something, I'm telling you which way it's going. That's really important. If you, like, especially non-physics people, the velocity is the way it is going. If I say which way is it going, I'm asking you for the velocity vector, okay? And if I ask you for the speed, I want the length of the velocity vector. So the velocity vector is really, really important. And its length you get with Pythagoras, that's speed, and the velocity I might give you, or I might give you some information so you can work it out. Now, you in the second year will need to use SUVAT with vectors a lot. It's called projectiles. And this is a second year thing, projectiles. And all projectiles is SUVAT with vectors. You could get SUVAT with vectors in the first year as well. You could just get, like, I could tell you the displacement as a vector. I could tell you the initial velocity and the final velocity as a vectors. And that's the initial direction and the final direction because it's changing direction. I could say that it's changing direction with a constant vector so that the SUVAT equations apply. Now find the time it takes. All of your equations for SUVAT still work apart from one. The one you can't use is b squared equals u squared plus 2as. We lose that one because you can't square a vector. So you wouldn't be able to do v squared. But everything else applies. And then the second year, when you learn projectiles, it is literally just SUVAT, SUVAT, nothing new. In the second year as well, you do variable acceleration in 2 dimensions or 3 dimensions. But it's just the same as the variable acceleration that you do in the first year. It's just, if you differentiate displacement, you get velocity. And if you differentiate velocity, you get acceleration. And if you integrate acceleration, you get velocity. And if you integrate velocity, you get displacement. Yeah, R is the vector of displacement, usually, R or S. So you might see here an R, RUVAT, instead of, yeah, no, you're completely right. R is a very common notation. And sometimes you might even see this. You might even see R for displacement. And then you might see this notation, R with a dot on it. That means that's a bit like, you know, we do like S prime to mean the derivative. It's like a prime. It means the derivative. And the derivative with respect to time is what it means. It specifically means dot means the derivative with respect to time. It's a specific notation. But you know this, right? You know how to get from displacement to velocity. It's the gradient, isn't it? Or in this direction, area under. So the area under the velocity, the integral of the velocity, that's the displacement. And the velocity differentiated, the gradient of the VT graph, that's the acceleration. So acceleration, you might see R double dot, the derivative of the derivative, a bit like F double prime. That's the acceleration. Anyway, we are drifting into the topic of variable acceleration here, which we're doing week after next. Acceleration. That's what we've drifted into. Meanwhile, no, variable acceleration is in the first year and the second year. When you do variable acceleration in the first year, all of your stuff is one-dimensional, so there's no vectors involved. So your displacement is going to be like s equals 3t squared plus 4t. So there's no vectors. The exact same topic is in the second year, but instead of the displacement or the velocity or the acceleration just being one function, y equals or s equals or v equals, it's a vector. So it's got stuff here and stuff here, but it literally is the exact same. You just do it to the top stuff and the bottom stuff. It's the exact same. So this is all second year, right? Apart from you do this in year one as well. What you will get is this in the first year, definitely. F equals ma. So it's still true that acceleration and resultant force are linked by Newton's law. It's still true. So look at this guy. If I do a force of 12 and a force of 10, if I put those on the end of each other like this, 12 and then 10, and that there is 30 degrees. Is that all right so far? Then this is the resultant vector, the resultant force. The resultant force is like the total overall effect. So if I do this guy there, and then I also do, have I got a nicer color? Yes. If I also do this guy, then the resultant force is the one going all the way through the middle. Now that's 30 degrees, and therefore this must be 150 degrees. And then I can find the length of the resultant force using the cosine rule. Okay, this one's length 12. This one's length 10. So I can find the magnitude of the resultant force using the cosine rule. And then I can write down Newton's second law, F equals ma. The force, that resultant force means there's an acceleration. If there's acceleration, there's a resultant force. And if there's a resultant force, there's an acceleration. So the law connecting those two is that the sum of the forces is the mass times the acceleration. And we know the magnitude of this force because we find it out here. And then that is equal to the mass times the acceleration. So if you divide under and find the length of the force divided by the mass, then you get the acceleration. So I needed to know what here? I needed to know that if you add up vectors, there's our 45 minutes. I needed to know that if you add up vectors, the resultant force is what you get on the end. You sort of like line them up on the end of each other, and then the resultant vector, the sum of those vectors, is going straight through the middle from the beginning to the end. And then cosine rule. So what is the summary of all of this about vectors? Let's go back to the very beginning, which is a song from The Sound of Music. Vectors. What we need to know, let's get rid of all of this, is that for the next 24 hours, you have got access to, or at least you will in a minute, because I don't think I've turned them on yet, but I'll turn them on in a minute. You have access to 24, 25, and 26, and you can make notes on all of this stuff. Second years, if you are watching this, I will also make the second year one, the 3D vectors. I'll turn that one on as well, just in case you want to have a look, but there's nothing new, okay? Further maths, I know and used to teach, but I don't have a course for it. And the reason for that is because of the options. So for me to do a further maths course, I would have to do all of the core, and then I'd also have to do the FP2 and the FP3 and the M's and the S's and the D's, because everybody can choose, your college can choose different options for you. So I'd have to do 7 or 8 times, well, you can work out how many different combinations are there that I would need to do. And then everybody would need those at different times, because if you're doing one, further maths in a year is like any A level in a year. Doing A level in a year is about 20 hours work a week for the entire year. So if you want to put in 20 hours a week, then yes, definitely. If you don't want to put in 20 hours a week, then no. That's how long an A level takes. 10 hours per week per subject for 2 years. Right, I'm going to finish this up now because we need to have our little break before I start the second years. So good luck with going through all that stuff. I hope that I've narrowed it down to this key knowledge. A to B is B minus A. What are parallel vectors? The fact that you need the cosine rule, the fact that you might still use F equals MA, and the fact that you need to know about direction and length using Pythagoras and using inverse tan. Okay. I will see you in MH. Oh, that's a good question. If you buy the maths course, can you ask questions on further maths? I'm going to have to, at the moment, the people who have it just ask questions. It is an A-level course, not a further maths course. What you'd basically be saying is, can you pay the money to tailored tutors, but then use the access to have me as a tutor tutoring you the further math stuff? And that would be individual tutoring, because nobody else in that course would benefit from it. So probably it's the sort of thing I would have to say no to, because it just wouldn't be feasible for me to be giving a load of, like now when people ask questions, everyone else can see the questions and everyone benefits from me going over answers. But as I say, with the further maths, I wouldn't be able to. Something I might be able to do next year maybe is to offer the core of the further maths, because at least then everybody's doing it. But again, it's at the moment, it's certainly not top priority. Right, I'm just going to add a thing in here. Whoops, there we go. Telling the second years what's happening. And first years, I will see you either at 4 o'clock for a study with me, or I will see you tomorrow at 12. No, I won't. It's Saturday. We get 2 days off. Yay. Monday at 12. This is today, Monday, 12 p.m. AS. All of statistics in a week. Right. Hello, second years. I'm just having my break. See you at 1 p.m. All right, because otherwise I haven't had a break, and that is not the rules of action hours. See you in a bit.